Hello and welcome back to my channel. We're going to be talking about concavity and points of inflection. So when we are dealing with our functions, our first derivative tells us about increasing versus decreasing, and our second derivative is going to help us with concavity. So we kind of need to talk about all the important features of a function, which for us are going to be critical points, intervals where we're increasing, decreasing, relative maximums and minimums, and then intervals where our concavity is up or down, and points of inflection, POIs. So this table right here kind of tells us all the different things that we can tell based off of if we know the derivative, something about the derivative, and what that means in our function. So if the derivative of our function equals 0 or does not exist, that means we have a critical point. If our derivative is greater than 0, we're increasing. If it's less than 0, we know we are decreasing. If the first derivative, f prime, changes sign from positive to negative, we have a relative max for f of x. And if f prime of x changes from negative to positive, we have a relative minimum. On the other hand, if f double prime of x is equal to 0 or does not exist, then we have a possible point of inflection. We won't know until we do some more digging. If f double prime is greater than 0, then we know we are concave up. If we are less than 0, we are concave down. If we change signs of our second derivative at these critical points, then I know that that is a point of inflection. So, in order to kind of do what we need to do, we're going to do a lot of the same things that we would have done with increasing versus decreasing, except for now we're going to do it with our second derivative. So, find the open intervals where f of x is concave up and concave down. Find any x values where f of x has a point of inflection. Give your reason. So this right here is f of x. So in order to find concavity, we need to look for those possible points of inflections, and that means we need to find the second derivative. So we're going to go ahead and find the first derivative. F prime of x equals 4x cubed minus 6x squared minus 24x. And then we need to find our second derivative. 12x squared minus 12x minus 24. So now what we're going to do is set this equal to 0. I know that this polynomial, this quadratic, is not going to have any undefined values, so we don't have to worry about that. We now just need to figure out when does it equal 0. The first thing that I'm going to do is make my life easier by factoring out a 12 from everything. And then I'm going to factor x squared minus x minus 2, which will be x minus 2, x plus 1. If I set both of these equal to 0 and solve, we get x is equal to 2, x is equal to negative 1. So 2 and negative 1 are my possible points of inflection. So now all I need to do is check to see if the second derivative changes sign at those points. I also need to figure out when we're concave up and concave down. So very similarly to my other table, I'm going to have f of x, f double prime of x, and x. We need to do all of our possible points of inflections. We found those at 2 and negative 1. So negative 1 needs to be on here, 2 needs to be on here. When those happen, our second derivative is 0. We need to then look at beyond each side and in between. So a number before -1, we're going to go with -2. A number between, I'm going to go with 0. And a number after, we're going to go with 3. So we're going to plug this into our second derivative. So -2 plugged into our second derivative. If I plug it in here, where it's going to be a little easier to do signs, this is going to be positive, so we don't even have to think about the 12. So we're just going to figure out the signs of these two. So -2 minus 2 is going to be a negative. -2 plus 1 is going to be a negative. So negative times a negative is a positive. If I plug in 0, I don't want to use the factor form. I want to use the standard form, because when I do and plug in 0, I get the y-intercept of -24. So it's going to be negative. And last 3, so 3 minus 2 is a positive number. 3 plus 1 is a positive number. Positive times a positive gives us a positive. So when I'm looking at this, I know when my second derivative is positive, we are going to be concave up. So we are concave up in this case. We're concave down in this case, and we're concave up. So just like increasing versus decreasing, we're going to be that concavity until we reach our 0, and then they make it to the next 0. So we are concave up when we are less than -1 and greater than 2. Because f double prime is greater than 0. We are concave down when we are between -1 and 2. Because f double prime of x is less than 0. And we also are looking for any POIs, so any points of inflections. So we have a point of inflection at -1 because we go from positive to negative, but we also have a point of inflection at 2 because we go from negative to positive. So we know we change sign at those 2 points, so I know that those are going to be points of inflection. Find the open intervals where g of x is concave up or concave down, and find any x values where g of x has a point of inflection on 2 to 2 pi. Give a reason for your answer. So same thing, we need to take the derivative. We have g prime already, so now we need to take the derivative of g prime to make it g double prime. So in our case, g double prime of x is equal to, we have chain rule here first, so 2 sine of x times cosine of x plus cosine of x. I see that I have a cosine in both of these, so I'm going to go ahead and factor out a cosine of x to get 2 sine of x plus 1. That multiplication is going to make things easier for me because we need to set something equal to 0. Sine and cosine are both continuous functions, so I know that this is continuous, so we don't have any undefined values, so I just need to look at when it equals 0. When I do that, cosine of x has to equal 0. Cosine of x is equal to 0 at pi over 2 and 2 pi. Well, I need to back that up already because I forgot to take the derivative of cosine. So we have some good ideas here, but it's not going to be helpful. Okay, so let's try this again. We have 2 sine of x, cosine of x. Now we need to take the derivative of cosine, which is negative sine of x. They both have a sine of x in common, so let's factor out that sine of x to see what we get. So 0 is equal to sine of x times 2 cosine of x minus 1. 0 equals sine of x. 0 equaling sine of x is even easier. 0 equaling sine of x happens when x is equal to 0, pi, and 2 pi. I only have to do those values because we're between 0 and pi. On the other hand, we have 0 is equal to 2 cosine of x minus 1. I'm going to add 1 over to get 2 cosine of x divided by 2. So 1/2 equals cosine of x. Cosine is equal to 1/2 when we are at pi over 3. And the counterpart of 5 pi over 3. So we have 0, pi, 2 pi, pi over 3, and 5 pi over 3. We need to check all of these values to decide if we're concave up or down and where we change signs. One of the things that we have to know is that we're not going to change signs on the endpoints. So we are not going to necessarily have to look outside of 0 and 2 pi. They're not going to be points of inflection on that interval, but we do need to check everything in the middle. So g of x, g double prime of x, x, we have 0, pi over 3, pi, 5 pi over 3, and the end cap of 2 pi. We need to pick some values in between because all of these are 0. In between these two values is going to be a couple different values. I'm going to go with pi over 4. The reason why is because pi over 4 is the same for sine and cosine, so it might just make it a little easier. In between pi over 3 and pi, we have 3 pi over 4 that I can use. Same kind of deal. Between pi and 5 pi over 3, I'm going to pick 3 pi over 2. I track back. I don't want to pick 3 pi over 4. I'm going to pick pi over 2. And in between 5 pi over 3 and 2 pi, I'm going to do the same thing that I did on the other side and pick 7 pi over 4. Okay, I'm going to do 2 pi over 3 and 3 pi over 2 first because they're a little bit easier. So pi over 2, when we're at pi over 2, sine is 1, cosine is 0. So we have 1 times 0 minus 1. 0 minus 1 is negative 1, so 1 times negative 1 gives us a negative. 3 pi over 2, we have sine of 3 pi over 2, which is negative 1. Cosine of 3 pi over 2 is 0. 0 minus 1 is negative 1. Negative 1 times negative 1 gives us a positive 1. Pi over 4. The big here is sine of pi over 4, although it is square root 2 over 2, is a positive number. Cosine of pi over 4 is 2 times the square root of 2 over 2. So we realistically have the square root of 2 minus 1. Square root of 2 is a little bit bigger than 1, so we have a positive number times a positive number to give us a positive number. 7 pi over 4. The y value is going to be negative, so sine of 7 pi over 4 is negative square root of 2 over 2. Cosine, on the other hand, is still going to be positive. So we get into that same situation of when it simplifies, we get square root of 2 minus 1. We have a negative times a positive, which gives us a negative. So we know we are concave up, down, up, down. So we are going to be concave up when we are between 0 and pi over 3, and when we are between pi and 5 pi over 3. And we know that this is true because g double prime of x is greater than 0. We are concave down on that interval of pi over 3 to pi and 5 pi over 3 to 2 pi, because g prime of x, or g double prime of x, is less than 0. And our points of inflection happen at pi over 3, pi, and negative pi, and 5 pi over 3. And that is because g double prime of x changes signs at those values specifically.